Welcome. Today, we are pulling back the curtain on something you literally use every single day: fabric. We're going to take a deep dive into the hidden, high speed mechanical ballet that turns simple threads into the clothes on your back.
Now, really, just take a second and look at the shirt you're wearing. See that intricate grid of threads? That didn't just magically appear. It was assembled by a machine, performing a series of perfectly timed movements, hundreds, sometimes thousands of times a minute. So, how does that incredible process even work? All right, so here's our game plan. We'll start with the basic players, the threads. Then we'll break down the core choreography of the loom, look at the essential backup systems, see how it keeps itself from making mistakes, and finally, we'll connect all that mechanical stuff back to the fabric you can actually feel.
Okay, so before we get into all the crazy action, let's meet the two stars of our show, the threads themselves.
At its very core, weaving is actually pretty simple. It's just the process of interlacing two different sets of threads, one going up and down, the other going side to side, to create a stable, flexible material. That's it. Now, these two sets of threads have very different jobs. The threads that run lengthwise are called the warp. You can think of them as the strong, stationary foundation. They're held super tight in the loom. They're the backbone. Then you've got the threads that run across the width. Those are called the weft. This is the active player, the storyteller, the one that actually does the weaving, going in and out of the warp to build the cloth. And now, for the main event. Creating fabric really boils down to three fundamental actions that happen over and over again in a super rapid, continuous cycle. This is the core dance of the loom. These three steps are what we call the primary motions of weaving: shedding, weft insertion, and beat up. You absolutely cannot make fabric without them. So let's break down exactly what each one does. First up, we have shedding. This is where the loom separates all those warp threads into two distinct layers, one on top and one on the bottom. And when it does that, it creates this little V-shaped tunnel, and that tunnel is known as the shed. The entire point of this step is just to create that little pathway. So, how does it do that? Well, the machine uses these things called harnesses. They're basically frames that hold on to the warp threads. And just like you see here, they lift certain threads up while keeping others down. This super precise mechanical separation is what makes that perfect little triangular shed for the next step. Okay, so the tunnel is open, and now it's time for weft insertion. A single weft thread, which is also called a pick, is sent flying through that shed from one side of the loom completely to the other. And the way that thread gets across has changed a lot. It used to be a wooden shuttle being thrown back and forth, but modern looms, they might use a tiny metal projectile, or a robotic arm called a rapier, or even incredibly fast jets of air or water to shoot that thread across at insane speed. And now for my favorite part, the most dramatic moment, the beat up. This is the forceful, powerful action that officially turns a loose thread into a real part of the fabric. The hero of this step is the reed. It's this comb-like metal part that swings forward with a whole lot of force. Its only job is to push that new weft thread tightly up against the edge of the fabric that's already been woven, packing it right into place. And we're not talking about a gentle nudge. This quote really gets it right. It says the action is so harsh that it earned the name beat up. I mean, think about that. It's this repeated, violent impact that compacts all the threads together and creates that dense, stable fabric we know. So, those three primary motions are the stars of the show, but they can't do their thing without a flawless support system. These are what we call secondary motions. They're like the unseen stage crew keeping the whole production running smoothly. And these two systems have to work in perfect harmony. On one end, you have the warp let-off, which is slowly feeding new warp threads from this giant roll, making sure the tension is always just right. Then, on the other end, you have the fabric take-up, which is steadily rolling up the brand new fabric. It's this perfectly balanced, continuous flow of material in, product out. But, what happens if a thread breaks? In a process that's moving this fast, one single broken thread could ruin yards and yards of fabric. That's where the auxiliary motions come in. They're basically the loom's automated quality control system. Modern looms have all these crazy smart sensors. The warp stop motion will instantly shut the entire loom down if even one of the thousands of warp threads snaps. And same for the weft. The weft stop motion detects if that thread breaks or just runs out, preventing a big gap. It's what allows these machines to run so fast with so few mistakes.
Okay, so we've got the whole process down, but how does this mechanical dance actually decide what the final fabric feels like? Let's connect these motions to the thing you can actually hold.
When it comes right down to it, it's all about this. The specific pattern of how those warp and weft threads cross over each other, the weave type, is what gives the fabric its personality. The more times those threads intersect, the more it changes the texture, the roughness, and the smoothness of the final cloth. Let's take a look. A plain weave, like in a basic cotton shirt, has a ton of interlacing points. That creates a more textured, kind of rough surface. A twill weave, just think of your jeans, has fewer interlacements. That's what creates that classic diagonal pattern and makes it feel softer. And then you have something like a satin weave, which has very, very few interlacing points. That lets long threads float on the surface, and that's exactly what makes it feel so incredibly smooth and flat. So the next time you put on a piece of clothing, just remember, it's not just a piece of material. It's the result of a perfectly coordinated mechanical ballet. It's a story of tension, timing, and force, all happening thousands of times over. And it really makes you wonder, right? What other everyday marvels of engineering are we completely missing?